to convince you too much on zero knowledge, but a lot of the work we've been doing currently has been on hash-based narcs. And I'm going to just give you like the very high-level overview or why we care about hash-based narcs and why they are like quite nice. So what do I mean by hash-based narcs? I mean snarks which are secure in the pure random oracle model. So I'm not going to allow myself any cryptography, no elliptic curve, no lattices, no algebraic assumption. I just want to use a random oracle. If you construct a snark in this model, you get like a lot of benefits. One of them is the fact that you can get like a transparent setup. That means that when I need to do the setup for like the snark, the only thing I need to choose is choose a hash. And if I have a problem with that particular hash, I can just choose it without having to go through any expensive procedure. Further, since this is just like random oracle, there's no lattice, there's no elliptic curve, there's nothing, I don't have to do any public key operations. So my prover can be fully implemented in, with the public key operation, so with the private key operation. So the prover can be extremely efficient. To give you like just some concrete numbers, this is something I ran on my laptop like, I think I did it like a couple of months ago, so it is possible that these numbers are outdated. But if you want to commit to the 26 elements with an hash-based scheme, you can do this in around 300 milliseconds. While if you're using an equivalent group-based commitment scheme, this will be on the order of 3 minutes on my laptop. So there's like a very important efficient difference between prover in hash-based schemes and other ones. So every benchmark is a lie. So this is also a lie, but this gives some intuition on why like hash-based proof systems have like very efficient provers. Further, we have extremely well understood security for like arguments in the random oracle model. We have bounds which are tight, and we can set parameters very efficiently. Finally, yesterday we had like a lot of talk about quantum, about the fact that this quantum day might be becoming very close, and hash-based narcs can be shown to be secure in the quantum random oracle model, which means that we can say that they are post-quantum secure. And all of these features have made the hash-based narcs to be like widely deployed in a bunch of applications, such for example, the biggest one currently by number of users is in Google Wallet. So I want to just give you a feel about what kind of parameters we can get for like state-of-the-art hash-based schemes. You can get like prover time, which are in the order of like a small hundreds of milliseconds to like a few number of seconds. Proof size ranges between 100 kilobytes and 400 kilobytes, and verification time can be from 100 microseconds to a couple of milliseconds. This in particular, the last one, we do not know how to achieve currently with any other assumption that is not hash-based. And there's been like, because of this, there's been like a flurry, like this, all these numbers come from like a flurry of works on like efficient hash-based proof systems. I've selected a few of them. I hope I've not slighted anyone about them. But if you look at these works, like there's one thing that jumps out, and it is that most of the progress in hash-based narcs in the past like 5 years has focused on getting proofs which are succinct. And zero knowledge is something that we actually need for a lot of application, and we know how to achieve it for hash-based narcs, but the generic way that we know how to achieve it with are usually kind of expensive. So in this work, we ask the question of, can we actually get zero-knowledge variants of these state-of-the-art hash-based narcs, where the overhead is like a low-order term on both the prover, the verifier, and the argument size. So I'm going to just jump into it and give you the results. So I'm going to assume that a few people here have been to IOP Fest. I'm going to still motivate the things, but we see that like hash-based narcs, they're based on like the interactive oracle proofs, and in particular, they're based on something called interactive oracle proof of proximity. And as our main result, we're going to present one of these interactive oracle proof of proximity for one class of codes, which are constrained codes. So intuitively, constrained codes are codes which admit, I'm going to introduce them properly later on, but which admit like a particularly simple folding operation. So here I'm going to give you the main results. So I'm going to try to get like an IOPP, which is going to be for Interleaved Rich-Solomon encoding. So n in this case is the number of coefficients I'm encoding. I'm encoding it in a domain of size m, and the interleaving factor I'm going to think as like a logarithmic, like a log n interleaving factor. And I want to achieve 2 to the minus lambda security. In the notion I really want is rump around security, but let's just say security for now. So, and I'm going to denote in red the overhead of like this proof system compared to the non-ZK variant, which in this case it would be like instantiation of WER. So the proof length, which is a measure of like the prover time, is the proof length of WER plus like a little of lambda with tilde, because we might have like some polylog factors in there of field elements. You actually get the same exact query complexity as the WER protocol. This is what translates later on into argument size for the compile argument. And both prover time and verifier time are essentially the prover time and verifier time of the non-ZK variant, plus a little of lambda, plus like some polylog factors in lambda. All of this while still achieving perfect honest verifier zero knowledge. So, when in reality this is just one instantiation of a framework that we built. If you've been to Ale's talk yesterday and to Produce talk yesterday, you see that like a lot of like the state-of-the-art IOPPs are built from like a general framework of reduction of interleaved codes. We actually do the same work, but we formalize this framework and we do it all in zero knowledge. And you get like, if you instantiate it, you get like zero knowledge over version of like existing protocols with zero overhead, including things like, for example, breakdown, WER, some version of Ligero, and others. And you might say like, look, Giacomo, why are we caring about honest verifier zero knowledge? It is because in the it's a black bar. If you have honest verifier zero knowledge in the IOP, once you compile it and you make the argument non-interactive, you get like malicious zero knowledge in the argument, or actually just zero knowledge in the argument. So further, like when we do this, our version of like breakdown achieve like some improved guarantees. So for example, we go back and we do like list decoding, and we achieve straight line knowledge soundness for all of this protocol. This is important for like things like for post-quantum security and UC security. Further, this is a generic framework which you can instantiate with any linear code that you want, as long as the linear code has a zero knowledge property. I'm going to talk about this later on as well. And finally, we also developed a framework for composing zero knowledge interactive work reductions. If you've seen William talks, interactive work reductions are a way to abstract like some of the common patterns in constructing the IOPs, and we show how to construct zero knowledge IORs. We show a toolkit for them and how to compose them while preserving a zero knowledge property. Okay, so look, this is somewhat of a practical conference, so you might ask us, okay, look, asymptotics lie, so what about concrete efficiency? And I'm gonna like do something a bit different, which I haven't seen in a lot of talks, and make the claim that we need to have better ways of comparing protocols, because modern protocols have a lot of parameters. And typically, there's like a very important trade-off between the prover time and the verifier time. If you want to think about Fry, for example, this is calculated by the rate of the code that you're using. So comparing protocols are not just 2 points in the graph. We really have to figure out what this trade-off is and what the protocols end up like achieving. And so what I'm going to do a Pareto frontier. So I'm going to plot this trade-off between two things which I can compute without having to implement things, because I'm really bad at implementing things. So I'm going to look at proof size, which correlates directly with prover time, and argument size, which is a good proxy of verifier time. So yeah, the proof size is directly proportional to the number of hashes the prover does, so it's a good proxy of prover time, while the argument size is the number of hashes that the verifier does effectively, and so it's a good proxy of verifier time. So if you haven't seen a Pareto frontier, this is what it looks like. So basically, there's going to be like this line. These are like the optimal points which achieve the best trade-off. So these are like the designs which achieve the optimal trade-off between prover time and verifier. Anything in the internal region we won't care about, because it will be dominated by things on the frontier. So, okay. Here's what it looks like. So the black line is a where, while the blue line is a ZUK. So I've helpfully zoomed in a little bit into this. So you can think of the area between the two curves is the overhead of adding ZK. So, it's not zero, asymptotically it is zero, but it is, I think, really acceptable. So for example, like if I look at this, there, the overhead is around 5-10 kilobytes for these sizes. These are for an argument of 2 to the 26 field elements. So, and once you go, like, once the argument size gets larger, this really goes to zero asymptotically. And this actually holds, like, for a lot of argument sizes. So here I plotted the Pareto frontier for many different argument sizes, and you can see that the overhead is almost a constant over like over the non-ZK version. Okay, so I think concretely this shows quite well. I also like these plots; they're a bit weird colored, but yeah, this shows how concretely we actually get like a very small overhead. So how do we do this? Now I'm going to tell you a bit like about the techniques to go into like achieving this. This is a bit of a weird talk because there was one at ZK Summit in which I covered some of the similar thing, but I'm going to tell you the roadmap, and then I'm going to focus on one component in constructing these zero-knowledge IOPPs. So if you've seen Alex's talk yesterday, you can see this is an instantiation of the same framework, but we're going to work in like a zero-knowledge like version of it. So we're going to have like two instantiations. One of them is the sublinear protocol, which is you can think it of as a zero-knowledge version of the breakdown protocol if you may it. And this is going to be built by composing a few different reductions. So first, there's going to be a reduction which just takes whatever relation you want, say a 1CS, and turns it into zero-knowledge problems about constrained interleaved codes. We're not going to see this at all. And then we're going to have a zero-knowledge sum check. And the way you should think about the zero-knowledge sum check is that it will reduce a claim on n coefficients to a claim on n over k coefficients, while making like O of lambda queries over an alphabet f to the k. So here's a trade-off between like how much you reduce the problem and how much the argument size goes up. And for the sublinear protocol, you should think of k to be around square root of n. Then there's going to be like a trivial ZK protocol, which has linear communication and verifier time, and we'll also have like non-zero overhead. But it's always fine to apply once the problem size has been reduced enough. Then we're going to build on these ideas, and we're going to do a subsyn protocol, which is a zero-knowledge version of where. So it's going to look almost exactly the same. So I'm going to still, again, apply like a ZK sum check, but now I'm going to set k to be logarithmic, so I'm going to reduce by a log factor. Then after you've done this reduction, you go from an interleaved code to a base code. So I don't have the ability to fold again. So what I'm going to do a zero-knowledge code switch, which I'm going to switch from a code to an interleaved code so that I'm able to actually fold again. And then I'm going to fold again with the ZK sum check, and I'm going to repeat this process roughly log n over log n times. And finally, at the very end, I'm going to apply this trivial protocol again. So in the last talk at ZK Summit, we should be online by now. We did the ZK sum check at ZK trivial. Today, I just want to talk about ZK codes and the ZK code switch together with the relation that makes these things work. Okay, so this is my plan. I think I will not be able to do all of it, but we'll see how far we go. So let me just do a little reminder of what error correcting codes are. We've seen a lot of these things before. This is just I'm taking a message and I'm adding some redundancy to it. In this talk, we're going to be focusing about linear codes only. And so I'm going to always denote by GC the generator matrix of the code. The map needs to be injective. The annoying part about error correcting codes is that they don't really, by default, give you some privacy notions. So if I am an encoding of a witness, which will happen in like these proof systems, and the verifier is going to query this encoding at some points, this can leak information about the witness. And in fact, in many cases, it will. This is a completely deterministic map. It's injecting. It will leak some information about the witness. And an example of where this is like problematic is like when you have a code with a systematic encoding, because they're like, look, the first half of the message is already like is just already the witness. So if I touch it, I will learn things. And this is suggest some notation that we're going to be used for later on. I just have it here on the slide for completeness. Okay, so we want to solve this privacy problem. We have this annoyance that like error correcting codes as they are, they don't give you privacy. How do you go and solve this? Well, there's a very beautifully and widely studied notion of zero-knowledge codes. Oh, sorry. So what are we going to do? For zero-knowledge codes, you want to solve the two competing constraints. So you want the code to still create distance. You want to create redundancy in the message. But you also want the reading code where should not reveal anything about the message, which are two contracted constraints. Okay, let's I don't know how to do this, so I'm going to look at the only thing that I know how to do, which is polynomials, and I'm going to think about with Solomon codes. So just to remind you what they are, these are I take a message, I interpret it as a polynomial, and I evaluate it over some subset of the field. So okay, here I've like I put 3 points in the field, and I'm showing you that with 3 points there's like a lot of like oh, what happened? Okay. There's like for 3 points, there are like a lot of quartics that pass by it. So, so for any like choices of point that you reveal, there's like many polynomials that agree with this. This is just interpolation. Like as long as the degree of the polynomial is larger than the number of points that are revealing, I can complete the curve in many different ways. Okay, we're going to use this to build like a zero-knowledge code. Which would appear in the slide eventually. Okay. So the way that I'm going to make a zero-knowledge code, a Solomon code zero-knowledge, is that I'm just going to like take the normal encoding and I'm going to add some randomness R. And this R will give me enough degrees of uncertainty so that like whenever I read a few locations of the code words, I don't learn anything about what the F was. And you can define like a zero-knowledge encoding property. And in this case, encoding will take like some message and some randomness. And we want the encoding to be that any like small amount of locations in the encoding are efficiently simulatable. Good. So this is the notion of a zero-knowledge code. Now we're gonna, and I'm also gonna use this notation that since like the encoding is a linear map, I can split the encoding matrix of the randomized encoding map into like one part which depends on the message and one part which depends on the randomness. This is gonna be useful for the code switch later on. Okay, good. So zero-knowledge code, this is all prior work. Now, I'm going to show you how to use the zero-knowledge codes to do a code switch. And before that, because this is somewhat new, I'm going to do a code switch again. So I'm going to start with like some linear claim about some code word F of some sort, so V and U. And I want to like change it to a claim about another code C2. It's like a version of the generic code switch that Ale presented like at IOPPs Fest yesterday. And the protocol is going to be exceedingly simple. So first, I'm going to ask the prover to send me an encoding of the same message F that was underlying the code word F under the different code C2. Then I'm going to do an out-of-domain sample. So an out-of-domain sample is something that we're going to be using for list decoding. And in a certain sense, it's going to pin down the prover to a single message underlying the code word is committed. I'm going to do a generic one where you just use a zero evader. This is not too important for now. You could think of this like just being like a univariate evaluation. And here's the definition of a zero evader. Okay, now I sent a code word. The prover, in a sense, committed to a unique message underlying the message it is sent. Now I want to make sure that there is consistency between the new message and the old message. So what I'm going to do, well, I'm going to do the only trick that I know, which is to spot check things. So I'm going to spot check things. So, and to do that, I'm going to query the original message as a few position. And what I'm going to do, I'm going to set constraints on what the new claim should satisfy. So we're going to have like an automate constraints. We're going to have the original constraints, and then we're going to have this constraint, which basically means that when I take the message encoded by G and I apply the ZIF row or the generator matrix, I get exactly what I read from the oracle. These are some problems. One of them, which doesn't have it, that this protocol is quite nice, is knowledge sound. So you get like some zero knowledge soundness, and you can actually play a lot around with what the distance parameters are in these errors. One problem that it has, it doesn't have zero knowledge, because this auto-domain sample leaks information about the message I'm encoding. This is not great. But this problem as a protocol has like an even worse problem in that it is actually not complete. Since we're going to need like our witnesses to be encoded with zero knowledge codes, the encoding map is deterministic. Is non-deterministic. So what I'm reading over when I'm reading from the original message will be randomized. So it needs to depend on the randomness of the previous encoding. And here we currently have no way of doing it. So no way of keeping track of it. So we need to have a solution in order to actually carry the randomness of the previous code into the code switch. Okay, let me give an attempt at this. So I'm going to be again in the same thing. Now I'm going to make it explicit that I'm using like a zero knowledge code for this encoding. And I'm going to do things in a very similar way. But now I want to use some randomness in order to make sure that I'm not leaking and that I can carry forward the randomness of the previous encoding. So I'm going to use 3 pieces of randomness, which have like confusingly similar names. Now, I'm going to do almost exactly as before. So the start of the protocol will be that I encode the old witness under a new fresh ZK code, which is C2. Now I need to do 2 things. I need to randomize my auto-domain sample, and I need to carry the randomness from the previous iteration forward in the code switch. So what I'm going to do, I'm going to use a second ZK code, SIDZK in this case, which will encode R, which is the old randomness, some new randomness M, which I'm going to use to hide the auto-domain sample, and then R double prime is going to be the randomness which hides this message. And I'm going to just send these 2 oracles now here. Of course, you can batch these things appropriately. Now I'm going to continue as before, so I'm going to actually just do a zero evader. But now when the prover does the auto-domain sample will actually be on the message encoded by the first code, and then the message encoded by the second code. So I'm going to do a joint auto-domain sample on both messages at once. Then I'm going to still do my spot checks as before, because I can read all of these and I'll be happy. And now when I'm going to just write down all the linear constraints which are induced on these joint systems of things. And now this new claim is going to be a claim on like both G and S, so like on both of these code words. So I'm going to continue with this, and I'm split things according to the matrix decomposition. Now, this might be a bit confusing, but you can, if you do the derivation, it's kind of like clear how these constraints came out. I'm just like rewriting f at zi using the encoding map of the zero knowledge code. Now, M can mask the auto-domain sample. In reality, you need some version of privacy from the zero evader because you want, for example, the contribution from M not to be zero out by the zero evader. So there's a version of private zero evaders that we define in the work. Now, the soundness error of this, well, it's a bit worse. Now you have like this, product of the list sizes, but it's not too bad because the zero evader error we can amplify as we want. So this is code switches sound. Good. How much am I doing on time? You have 3 minutes. 3 minutes. Okay, good. Good. So this is going to be the old code switch. Like with this, like we can see, we have basically done the entire protocol between the ZK Summit talk and this talk. So I'm going to just show you like we're going to ignore that. So I'm just going to tell you the relation that we care about in this work is this joint constraint relation, because as we saw before from the code switch, we don't have now the luxury of only having constraints which are on a single code word, but we want to think about joint constraint about messages encoded by different code words. So here's what the relation looks like, and I'm going to just walk through it quickly. So you're going to have a constraint, which in this talk, I'm just making an explicit vector v. And you can make a certain description out of it, of course. You have a valuable constraint mu. You're going to have code word f and s. And your witness is going to be the messages and randomness used to encoding the entire f and s. So this is not a pointer. Or is it a pointer? It is not a pointer. So the relation is about like f and s, which are honest ZK encoding, such that the joint message by f and s satisfies some linear constraint. So this is what we deal with throughout our reductions. So exactly. So, and we call this a joint constraint. So okay, now I'm going to just give it back. This is my last slide. So Elon is happy, reasonably happy, and I'm going to just tell you how we put everything together. We get the succinct protocol. Okay, so I'm going to start, and I'm going to start with a interleave code with interleaving factor to do decay. So we haven't seen it in this talk, but I'm going to do the zero-knowledge sum-check protocol, which you should think about it as a sum-check protocol a la Libra, where I'm using like some masking to mask each of the sum-check polynomial. So this is the masking that's done. And I'm going to apply like k rounds of sum-check. Each of them will reduce the problem size by a factor of 2. So overall, I'm going to reduce by a factor of 2 to the k. At the end of this sum-check, I'm going to define a virtual oracle, which is the fold of the original oracle on this part. So this reduces by a log n factor with 0 overhead by prior work, which I'm not mentioning, by prior talks. Then I'm going to apply the code switch. So I have this fold. This fold is encoded under the code C. And now I want to code switch to a new interleave code so that I can fold again. So I'm going to send the re-encoding of the fold under F1 plus the masking that we saw before in the code switch. I'm going to do the auto-domain sample. And then I'm going to query the fold. This is going to be reading all of lambda queries, each of them of an alphabet of size 2 to the k. And I'm going to switch in ZK to the interleave code. Then I'm going to apply the ZK sum-check. And I'm going to reduce and repeat this for a bunch of times. And finally, I'm going to send like the final oracles for this trivial protocol, where essentially I just mask whatever at the end. And this is fine because you're going to pay some overhead there, but the size of the instance at this time is kind of like O of lambda, is tiny. And if I look at the complexity, roughly, again, the red is the overhead. So the query complexity overhead is just the query that you have to do to these new ZK code masks, which with a setting of parameter, this is like little O of lambda, so it is negligible. And the proof length is just basically added by how large the ZK codes are. And again, with setting parameters, probably this is like little O of 1, less overhead. Good, so yeah, this is all of it. And I'm sorry I had to piece it from different talks, but I think, yeah, this is overall the entire protocol.
A quick question.
Thanks. RS code, of course, is a zero-knowledge code, but I'm wondering if the breakdown-like code or Spellman-like code are also zero-knowledge code?
Okay, yeah, so that's a good question. So the breakdown code, if I remember correctly, is systematic, so it cannot be zero-knowledge. And we know some linear time encodable zero-knowledge codes, such as, for example, those in BCL. Unfortunately, I think that there aren't that many of them. And I think a very interesting open question is figuring out which other linear time encodable codes are zero-knowledge.
Okay, thanks.
Okay, let's thank Giacomo again.
Thank you.